Okay, hi everybody, good morning. As promised, here's the video that explains the answer key to this activity number 38, finding genotypes and phenotypes for one trait. I apologize for not posting this earlier. It was giving me a hard time uploading it. So here we go. I'm not going to read the whole front. This would be a good time for you to grab this sheet and have it in front of you. Pause the video as you need to, and let's take a look. Okay, so grab the sheet so that you can read it better. On the first page where you had to actually fill in answers, we have just real simple different phenotypes and genotypes. They gave you certain information, you had to fill in the rest. Pretty straightforward stuff here. Again, two dominant alleles we would call homozygous dominant, two small or recessive alleles we will call homozygous recessive, and one of each allele we will call heterozygous. Remember, you only need one dominant allele to have the dominant phenotype, which is physically what you see. Remember, phenotype is physical trait. Okay, down in here, super simple stuff. I'm not going to go through everything detail by detail. We're going to focus on ratios in this part here. This is what Gregor Mendel focused on when he was doing his research on pea plants. The ratios really tell the story. First, they asked you to take a homozygous green and a homozygous striped watermelon here in number one. Again, dad's alleles go up here. He only has dominant alleles, so half of his sperm will get a dominant G, and the other half of his sperm will also get a dominant G or green allele, because that's all he has to give, because he's homozygous dominant. We would call him a true breed, by the way. Mom is striped. The only way to be striped is to be double recessive or homozygous recessive. So mom's egg cells, again, are only going to get 50% of her genes. So one egg cell will get one little G, and the other egg cells will get another little G. Really, a better way to say that is 50% of her eggs will get a little G, and the other 50% will get the other little G. Keep in mind that mom got one of these from her mom and one of these from her dad. Keep in mind that dad got one of these from his dad and one of these from his mom. Now, in the ratios, we work out the Punnett. As you can see, these two parents will always have kids that are heterozygous. We talked in the last video that probability in these Punnett squares, and these are prediction, they don't always match real life, but sometimes they do. In this case, these two parents will always have heterozygous children forever and ever and ever. They cannot have any other combination. So let's look at the ratios now. This is the important part of this lab, or this activity. Genotype and phenotype ratios. Every time we write these, they're in the same format. Please pay attention to this. Every time we write these are going to be in the format of, for the genotype ratios, how many homozygous dominant, how many heterozygous, and how many homozygous recessive. So when we look at these numbers up here, 0 to 4 to 0, the order that you write those in is very important, because we're saying these kids, this F1 generation here, remember the parents are the P generation, the first set of kids are the F1 generation, and then the grandkids over here would be the F2 generation. So when we write these ratios for a genotype ratio, we're saying how many were homozygous dominant? In this case, none. How many were heterozygous? In this case, all 4. And how many were homozygous recessive? In this case, none again. 0 to 4 to 0 genotype ratio. Notice that adds up to 4, because there was 4 kids that we were making the prediction for. Again, this is prediction probability, not necessarily reality, but in this case, it would match up. For phenotype ratios, down here, I left you a little note. Phenotype ratios, you're going to go with, there's only 2 phenotypes in this case, either you're green or you're striped, and that's either your dominant or your recessive. So how many dominant compared to how many recessive? That is this format right here, this ratio format right here. How many were green, how many were striped? Well, as you can see, all 4 of these children are green and none of them are striped. So the phenotype ratio, again, only contains 2 numbers, is 4 to 0 in this case. Notice that also adds up to 4, because we have to account for all 4 children. Okay, so I hope you have that format kind of etched in your head by now. Also, it asked you to take any 2 of these kids and now make them parents over here for the F2 generation. Okay, so again, we had the parent generation here, the original mom and dad. We had the first set of kids, the F1, and now we're going to take 2 of these kids and make them parents over here. Remember, this is plants, so it's okay to breed family members together. So now we're going to have the F2 generation. Think of these as the grandkids. we could take these kids and breed them together and make an F3 generation, which would be the great-grandkids, and so on and so on, okay? So for this one, we had a couple of heterozygous children from here that now became parents over here. When we breed them out, again, very simple stuff, here's what we get. Here's what we would predict we would get, I should say. For the genotype ratio, 1 homozygous dominant, that's that kid there, 2 heterozygous, that's there and there, and 1 homozygous recessive, that's right there. Again, these numbers add up to 4. For phenotypes, if you look closely, each one of these 3 boxes has at least 1 dominant gene in it, or 1 dominant allele. That's enough to make them have the dominant phenotype. Remember, you only need 1 dominant allele. So if we look at phenotypes, we would see that 3 of these are going to be green and 1 is going to be striped. So that phenotype ratio is 3 to 1. Again, that adds up to 4. Now, looking at these ratios, here's the important part. Mendel saw these ratios and was able to kind of figure backwards what must have been going on with these genes. Keep in mind, he didn't have any idea about alleles or genes or DNA or anything yet in the 1800s when he was doing his work. Also keep in mind that typically when you see a plant or when you see any organism, you're looking at its phenotype. You don't necessarily know its genotype. So Mendel actually paid extra attention to these phenotype ratios because that's what he could see. He could then maybe figure backwards based on what he was getting, his results, from each cross that he did or each breed that he did when he bred 2 things together. He could kind of figure out what must be going on by the ratios he kept seeing. Also notice, when you have 2 homozygous parents over here, you're going to get ratios like this, 0 to 4 to 0 and 4 to 0. When you have 2 heterozygous parents, you get different ratios. These ratios are almost like a signature or a fingerprint for what the parents must have been. Keep that in mind because that's where the devil's in the details on this one. Okay, next page. This one got a little cut off, I apologize, but again, you have this in front of you. This is talking about how to test cross organisms that you do not know their genotype. So for instance, if you looked at somebody with brown eyes, you might see their brown eyes, their phenotype, but you wouldn't know if they were big B, or if they were big B, little b. So there's a way to test that. And what we do is we take different organisms and we always, scroll up here. I'm doing this bottom part right here. I'm not going to do this top part because it was pretty straightforward stuff. And there's the answers for you. But for the test cross, what we're talking about is how to determine what the genotype of an unknown parent is by looking at his children. So here they talked about 2 unknown genotypes. We didn't know what the parents were, so we want to test cross them with a known genotype. Well, the known genotype is always going to be a double recessive, because if I look at something that's got 2 little recessive alleles, think of 2 little B's for blue eyes, for instance, I not only know the phenotype, but in that case, I also know the genotype. However, when I look at a dominant phenotype, for instance, brown eyes, I do not know the genotype necessarily, but I do know the phenotype. So for a test cross, what they've done here, or what we're always going to do, is we're going to look at the different possible situations and look at the ratios, and then we can determine what the original parents were. So if my original parent was disc-shaped, that's the dominant allele here, we don't know if he is big D, or if he is big D, little d. We don't know. So what we'll do is we'll cross this parent with with another parent that is homozygous recessive. We know this phenotype and this genotype because if you're little d, you must be sphere shaped. Okay, so that's the going to be the summary of test crosses. Always cross with a homozygous recessive parent to see what comes out in the children. Then we can figure backwards what the original parent must have been over here, the unknown parent genotype. So when we do it this way, we would expect to get all 4 heterozygous children, and all 4 phenotypes would be dominant. So these ratios would be here. So if you saw something like this appear, you'd be able to say, oh, that original unknown parent must have been homozygous dominant. Now, on the other hand, if the unknown parent was heterozygous, we would expect to see different ratios when we test cross the organism with a homozygous recessive Again, the commonality here in a test cross, always crossing with a homozygous recessive, here and here. If in fact the parent that was unknown is big D little d, heterozygous, still dominant phenotype, we would expect to get these ratios, 0 to 2 to 2 and 2 to 2. So as you can see, the ratios kind of tell the tale of what the parents must have been when we don't know that information. So keep that in mind. All right, next page. Sorry about the chicken scratch on here, but I think you can kind of make sense of it. Again, you should have this in front of you as well. For number 1, it just said compare the phenotype ratios for part A and B, for steps A and B in part 2. Well, part 2A, ratio is 4 to 0, phenotype ratio. Remember, it's 2 numbers in the phenotype ratio. And for part 2B, it was 3 to 1. And that's because the parents were different, so you would expect different ratios. If you look at number 2 here, compare the phenotype ratios obtained in step B and D of part 2. Well, if you look at them, part 2B was a 3 to 1 ratio, and part 2D was also a 3 to 1 ratio. And if you go back and look in the worksheet, you will see the reason these ratios were the same is because they were really the same parent type combinations. Okay. All right. Number 3, if a farmer wished to produce only disc-shaped squash, what should be the genotype of all parent plants? Well, if you want to keep producing the same phenotype, you want to make sure you're using homozygous stuff. Especially in this case, so you wanted to keep producing the dominant phenotype, so use the homozygous dominant parents. So if all parents are always big D, all children will also be big D, and therefore they'll be this shape forever and ever and ever. This is kind of how dog breeders do things, and certain farmers when they're breeding things, or ranchers when they're breeding cattle. They always want to get the same outcome because they want to have a consistent product. All right, number 4. Excuse me. How could a guinea pig breeder determine whether a rough-coated guinea pig is homozygous or heterozygous? Well, here we go again with this test cross business. We want to know, how can we determine an unknown parent's genotype when we only know that he has a dominant phenotype, rough-coated with dominant? And again, what you want to do is you want to perform a test cross, just like we just did, with a little r, a homozygous recessive, smooth. That way, we will look at the ratios and we can determine what the original parents should have been. This is not always exactly perfect, again, because it's based on probability. But for instance, if you saw any children that had the recessive phenotype, you would automatically know as soon as you see one kid born in real life with the recessive phenotype, you could be sure then that the original unknown parent must have been heterozygous. Okay, that's the whole kind of point of a test cross, determining what the original parent was when you didn't know it. All right, number 5 is a pretty heavy-duty question. If you got this one, or even if you got parts of this correct, you are really rocking. Let's have a look at this a little bit closer. A brown mink crossed with a silver blue mink, brown was dominant by the way, produces all brown offspring. So that right there gives you a hint. If they're all brown offspring or kids, you know that the brown must have been the dominant. When these offspring are mated, they produce 60 brown minks and 20 silver blue minks. Well, if you're kind of a math person, you can probably start to see that that's a 3 to 1 ratio. 6 to 2 is the same as 3 to 1. Keep that in mind, because remember, ratios like these up here kind of tell the tale of what the parents must have been. So which trait is dominant? Well, brown, of course, because the first F1 generation turned out brown. What are the genotypes of the P generation? Remember, the P is the original parents. That's the first generation. What must have been their genotypes? And we'll come back to that in a second. And then what are the genotypes of the F1 generation? That's the first set of kids. How many of those 60 brown minks in the F2 generation, again, this is the grandkids, would you expect to be heterozygous? So let's scroll down here a little bit. I gave you some hints, and obviously there's all the answers right here. Brown is the dominant trait, and we know that because all the first kids were brown, okay? 60 brown and 20 silver blue was a 3 to 1 ratio. That was the F2 generation. Keep that in mind. The P generation genotypes, the original parents. In order to get these kids here, In the first generation, the parents must have been big B times big B little b. That's what it had to have been. Otherwise, we would have seen different ratios. The F1 generation, remember the first set of kids, phenotypes were all brown. They told us that anyways. And finally, if you look at this 60 to 20 ratio, if you look at the 60 to 20 ratio, I'm going to scroll down a little bit. Here is how I kind of came up with some of these answers. So look at number 5 right here, down at the bottom. Here must have been the P generation. They must have been homozygous dominant times homozygous recessive. I apologize if you can't see that right there. Try to get it up a little further. Try to X out of that maybe. Okay. Homozygous dominant times homozygous recessive. That would have given me an F1 generation of all heterozygous but still dominant phenotype children. Again, these are the F1 generation kids. These are the P generation parents. We got a 0 to 4 to 0 ratio there and a 4 to 0 phenotype ratio. Now take 2 of these kids and make them parents over here, just like we did in the last part of the activity. And what we're going to do is we're going to take them and cross them 2 heterozygous times, a heterozygous times a heterozygous, I should say, and we're going to get a different set of ratios here. We're going to get a 1 to 2 to 1 and a 3 to 1 ratio on these F2 children. All right, so that's kind of how we generated these answers up here. Finally, 40 out of 60, that's 2 out of 3. 2 out of 3 of the brown minks were in the F2 generation were heterozygous. How did I figure that out? Well, 2/3 of the 60 equals 40. Remember, we said 2/3 of the 60 that were born, which is what they give you in the information up here. They talk about the 60 and the 20 up here, okay? 2/3 of those, 2/3 of 60 equal 40. That's a tough question. Finally, going backwards a little bit, number 4, that test cross that we performed is performed down here. The test cross is performed down here. We did not know this parent. Remember, that's what a test cross is for. So we always test cross against a homozygous recessive. If we see all dominant phenotypes, we can probably say that the original unknown parent was homozygous dominant. However, if we see even one child born with the homozygous recessive phenotype, then we can say for sure that original unknown parent over here must have been carrying the little r, must have been recessive. So the minute you see a child born with the recessive phenotype, it's a dead ringer that you are certain, you are sure that the original unknown parent, whose phenotype we knew but genotype we did not know, must have been heterozygous. This is also the example I gave in class with my wife and I. We are both brown-eyed parents, and we had a blue-eyed kid. When our son Max was born with blue eyes, that told my wife and I that we must both be heterozygous brown eyes. Again, looking at us, you only know our phenotype, but when my son was born, he told us, or he really confirmed what our genotype was. We didn't know that before we had our son. His blue eyes must mean that my wife and I are both heterozygous. We're carrying a little blue gene, but not expressing it. All right, so I hope that helps. Stay tuned for the PowerPoint coming up very shortly. Have a great day, everybody. Stay safe.